Hello GGS 300 and welcome back. This week it's lecture 14. We're going to be focusing on regression, and for many of you I know you'll be glad that we're basically almost at the end of the course now. So this is the last week of lectures, so you'll be free once you've managed to basically complete the final assignment, which I'll be setting you today, which will be due on December the 9th. And then we'll just have the final exam, which is going to be due by December the 14th. So this is currently still a preliminary date, but I'm pretty confident that that's when we're going to have the final submission for the exam, and I'll set it so that you have basically from the 9th to the 14th to complete it, and then that gives me basically about 24 to 48 hours to turn those marks around and submit the final grades. Okay, so in this lecture today I'm going to give you an overview of regression. And then in the second part of this lecture, I'm going to give you a bit of a recap on what we've covered over this entire semester in this class in order to prepare you for what's going to be in the final exam, okay? Great, so I think that all should be fairly self-explanatory, and I do hope that you've enjoyed this course. I do feel that the content within it will really put you in a good place in order to enter into the job market, okay? So let's get stuck into regression. Most of this we know now are on this formal hypothesis testing, although most of what we've covered here has generally been focusing on single samples or maybe two samples, maybe for different categories. But one of the most powerful tools that we have is when we actually use what's called regression analysis, and this allows us to have up to as many independent explanatory variables as we like in order to try and understand causally how those variables may affect a single output that we're interested in, okay? So now I think we've covered pretty much everything that's on the flowchart within the slides, and all we have to do is just wrap up this part now. So let's just quickly recap, because I mean regression is kind of the pivotal topic that we have within the course, and it's something that's really a strong method. And I just wanted to make sure it kind of sinks fully in before we get into some of the content. Okay, so the basis of statistics is that we have some sort of outcome variable, for example income, and that we have some sort of model that we want to fit. Maybe that's a variable such as the number of years of education that you've had, and then we have an error term. So this is basically all of the amount of variance in the outcome variable that the model, for example the number of years of education, hasn't been able to explain. Okay, so if I was to say to you that we were going to take years of education, you would probably expect that people with fewer years of education would end up having a lower outcome in terms of income, whereas people with more years of education would end up having a higher salary at the end of the day, okay, higher income. And basically, if we just took that very simple model, everything that isn't explained by the number of years that you've had within education would be within that error term. Okay, and this is basically the simplest possible way for me to explain the basis of statistics to you. Okay, we want the largest amount of data explanation using this model here and this to explain the outcome variable, but we want to use the least number of predictors possible. Okay, so preferably just one predictor is the simplest way potentially to predict your income if we just take the number of years that you've been in education. And what we do basically is we take the test statistic in any of these models, and you'll be very familiar with this as a very kind of nuts and bolts level, because we've done this in pretty much all of the tests. So we've taken the variance explained by the model as this numerator, and then we've divided it by the variance that the model has not been able to explain. Okay, so we have the effect over the error term in order to give the test statistic. So let's get stuck now into simple linear regression, and this is going to be what's called the least squares estimate of the line of best fit. So the question is, well, what is the form or nature of the relationship between the variables which we're going to study here? And we can keep using that kind of example, which is the number of years that you've had in education versus the income which you eventually command when you go out into the market, the labour market, and look for a job. So like correlation, we're measuring how one variable relates to another. So our question here is, well, how does the number of years that you've had in education actually affect your income level over your lifetime or starting job salary? So we have the difference between the work that we covered essentially last week, and that was just looking at correlations, and the work that we're going to cover this week, which is regression. Okay, so in the correlation analysis, we were looking at basically the strength of certain relationships and the direction of those relationships between two variables. Whereas in this, what we're doing with regression is essentially we're looking at the functional relationship between those variables. So for example, with correlation analysis, we were looking at, you could look at income and the number of years that you've been studying. That would just indicate basically a kind of a positive correlation between the two. And that's fine. And we know theoretically that they would be kind of related, and therefore it makes sense to kind of look at the correlation between them. Obviously that doesn't necessarily mean it's causation, and while causation is hard to prove, at least with regression analysis you have a more functional way to say, well, this is our output variable, our outcome, our dependent variable, and then we think that the independent predictors that we're going to put into that model are basically going to explain the variance in that outcome model. So it provides us with more of a causal attempt to basically try and understand some sort of phenomenon of interest that you're focusing on. So both of these approaches measure the degree of association between the variables, but the correlation analysis only measures the strength and direction, whereas what we're doing with regression analysis is to actually try and look closer at the functional causal relationships that tie several variables together. Okay, so the regression analysis needs to actually specify which factors should be X, so basically the predictor variables, the independent variables, or Y, so the outcome variables, the dependent variables. Okay, so we'll get more into this week so that you understand exactly the differences. Basically, regression analysis is a quantitative way to look at variables when you have one or fewer variables influencing or affect or another. Okay, I think maybe that should be one or more variables. One or more variables influencing another. So apologies for the minor rewording there. But essentially you have these two factors. So you have the dependent variable, which is the Y, and then you have the independent variable, which is the X. So basically the dependent variable is the variable that we're going to use as the outcome effect. So let's say it's income. Whereas with the independent variables here, this is basically the influence of that variable. So that's basically like the number of years that you've been studying, for example, in education, which could range from 7 to 10 years all the way up to 20 years if you were to go on to PhD and postdoc, essentially. So, and I've written a few of those examples down here, and we've been over the first one quite a few times. Another good one, of course, is my classic farmer's example, which I've used a few times in the course. So imagine you're trying to grow some crops, and your yield, so the amount of, let's just say, sweet potato that you grow per square hectare, that's going to be dependent on a wide range of factors, but one of the main factors that could influence that is the amount of fertilizer that you use, and therefore in that case our dependent outcome would be the yield, so the number of sweet potatoes that you grow per square hectare, and then the independent explanatory variable would be the fertilizer usage per square hectare, which would probably have a very strong positive correlation on the amount of yield that could be produced. Okay, so we have a model, so an input variable here like fertilizer, and then we tried to use this to explain the outcome variable, the number of sweet potatoes that we produce, and for all of the variance that isn't explained by this input factor here, which could be one or more factors, basically we capture that in an error term, so it's everything that's not explained by the model. So we are hypothesizing that the dependent variable is influenced by the independent explanatory variable, okay? So we're using as predictors these independent variables that sit on the right hand side of the equation. So all of the ones that are basically X are the independent variables, and they're trying to explain what's happening in the output variable Y. But first we must obviously kind of visualize the data. So this isn't the first time that I've said this. I've said this many times in the course, which is before you start doing the fancy statistical analysis, you need to make sure that you actually visualize that data, okay? So what you would want to do is you want to maybe carry out a bivariate linear regression, which it helps you understand the linear functional relationships between two variables. So here we might be asking, is there a relationship between the number of years that you study in education and then your income? And obviously this is education down here, and this is your income level. So maybe we have 10 to 20 years, 30 years, depending on how many years you've been studying. And then you have your income level here, $50,000, $100,000, whatever. And what we're going to do is we're going to try to fit this line of best fit between all of the points, okay? And what we're essentially going to do with the predictor variable is for every 1 unit increased in the number of years of education, for example here, we're interested in how much that changes on the y-axis. So for every 1 unit increase in x in education, how much does that change on the y-axis, the actual income that you could potentially earn? And by fitting this line, you're able to get that understanding. Okay, so y equals a, which is the intercept, the point at which the best fit line crosses the y-axis, plus b, which is the beta coefficient. So basically it's the coefficient value here. It's the amount that for every 1 unit in x you get a corresponding increase in the y variable. Okay, so a and b here are the constants. A is the intercept of the line and b is the slope value, which I've just been talking about. So for an increase of 1 in x, we have an increase of y in the other variable. So least squares regression, so this is when we need to estimate the values of the intercept and the slope, okay? So least squares, best fitting or regression lines. So the best estimate of the relationship between x and y can help us basically produce a predictive model, okay? So once you've got this relationship, which I'm talking about here, and you fitted this line, it doesn't matter that you don't have data points for all of these other places on the line. You can just take that functional relationship and use it as a predictor. So let's say that we have someone who has 25 years of education here. We would be able to then follow that across to a point on the y-axis and make a prediction about the expected income level that we would expect if someone had that number of years of education. Okay, so it's a very, very strong tool. The best fitting line is the one that minimises the sum of the squares, so the vertical distances between each one of the points and the line that we're fitting. Okay, so this is a good example here. So we're minimising these D1 distances, D2 distance here, D3 distance. So this is the least squares regression. It's just trying to find the optimal minimal quantity which draws a line between all of these points. And you can see the math here. So I'll get into this very shortly. For a specified candidate line, so you've got the output variable, given any x value, so this is what I talked about before, we could then calculate a predicted value, so the y hat, okay? And then once we've got that, that can tell us something interesting. We could use that to predict income based on education levels, or what we could do is, well, obviously we're going to need to fit that line of best fit, okay? So the y here is the predicted value, and you're subtracting it from each of the y values that you've got. So you're getting the deviation squared and then summed across all of these data points, okay? And then you want to minimize that quantity, so you want to minimize the variance between the predicted values along the line. Now look, there's multiple complicated ways that the book actually calculates the A and the B, so the alpha and the beta parameters for our model. Now I'm not going to force you through this, as we've got more simple ways to do it, but I just want you to remember that the A is the intercept, so the point at which the line crosses the y-axis. It's the value that would be there on the y-axis, and then the beta is the slope coefficient, okay, the regression coefficient. You know, one of the problems in statistics is there's multiple names for the same term, unfortunately. So our book calculates A and B in a rather complex way, okay? So we've got an easier way that I'm going to show you here. So basically, to get the alpha, so the intercept value here, you can take the mean of the y values and subtract the beta multiplied by the mean of x. Okay, and then you're going to ask me, well, how do you get the beta ed? You haven't stated it yet. And over here, what you're able to do is to get the beta coefficient by basically taking the correlation coefficient r and multiplying it by the standard deviation, the y value, divided by the standard deviation of x. And that gets you the beta parameter. Okay, so nice and easy. These aren't complicated equations. They're just two simple stages in order for you to get them. Thankfully, most of this hard work, well, pretty much all of it, is going to be carried out by R. So you're not even going to have to do this. You just need to know how to actually do this. Okay. So A is the intercept, as I mentioned. B is the slope. With the slope, if you have a B that's positive, that would indicate that you have a positive correlation. If it's negative, it would indicate that it's a negative correlation, and if your beta coefficient is basically 0, then you've got no relationship between the two variables, which is a bad thing. You need to respecify your model, remove that predictor because it's not adding anything to your actual model. So the coefficient value signifies how much the mean of the dependent variable changes given a 1 unit shift in the independent variable. Okay, so holding all other variables in the model constant. So economists will call this ceteris paribus, basically with all things being equal. And this kind of idea of actually being able to hold some of the variables constant within the model while you look at the effect of each of the individual variables in isolation is kind of critical. It's kind of central to how we do statistics, and it enables us to have this kind of causal understanding of potential phenomena of interest that we're producing, and then actually potentially produce predictions for what we think those future states of that outcome variable may be based on combinations of input factors. Okay, so let's focus now on the bivariate regression analysis. So this is basically trying to use regression in an inferential way. So the objective is to determine if x accounts for a significant proportion in the variation of y. So you need two random samples, and you need to make sure that you actually had an x and a y variable which had a linear relationship between them. We would need to make sure that our residual errors are actually normally distributed in order to comply with the requirements of the assumptions of the test. We need to make sure that we actually had an equal variance for all of those residual errors, and we need to make sure that the residuals aren't dependent on each other or another factor, so we need to make sure that they're independent. And then finally we need ratio or interval data. Okay, so basically in the hypotheses, in the null hypothesis case, we're basically saying that this p value here, this p squared population coefficient of determination, is equal to 0, so there's no relationship, whereas in the so no relationship between these two factors, whereas in the alternative hypothesis what we're basically saying is that they are different from 0. There is a relationship, we just don't know whether it's positive or negative. Okay, so it's just significantly different. And here we're going to be using the f-test. We do this because we've got multiple factors, so it's based on the similar approach to what we did in ANOVA. And basically we can get this f here by taking the sample coefficient of determination, which is this r squared value here, multiplying it by the number of degrees of freedom, so n-2, and dividing by 1 minus r squared. So how do you get the r squared? I hear you asking. Well, basically what you can do is you take the sum of the explained variation divided by the sum of the total variation, okay? And I'll tell you how to do that very shortly. So remember that the total variation in the data is basically the explained part, the model, plus the unexplained part, which is the error term, okay? So the total sum of squares, this TSS, the total variation in y, is equal to the explained sum of the squares through the regression, this RSS value, plus this error term, which is the ESS, so the unexplained sum of squares from the estimation that we've carried out. So basically what we're able to do to get the total sum of the squares is you take the sum of, and y bar is obviously the mean, we're subtracting it from each of the yi individual data points to get the deviations, and we're squaring them and summing them, and that gives us our total sum of squares. The explained variance is basically the mean value of y subtracted from each predicted value of y to get the deviations squared and summed. And then the error term is basically the predicted values of y subtracted from each of the yi values squared and summed. Okay, so we'll come back to that. This is kind of three fairly central techniques in order for us to carry out this assessment. So the fit part is also called the explained variation. It's the amount of variation that can be accounted for by the independent variables that we put into the model. Okay, so we have this dependent variable y, then we have this x variable or other x variables that we put in that then explain that part. It's the amount that's fitted in the model that gives us the amount of variation that our model is able to explain. So the residual part is basically all of the unexplained variation that's in the error term, okay, and that's the amount of variation that basically our input factors don't explain in the outcome, okay. So the deviations of the data, so the residual part is basically the deviations from the data and the points from the line, and the residuals are basically the observed response minus the predicted response, and it gives us a mean residual value of 0. If this is if we're complying with the assumptions of the actual statistical approach, okay. The coefficient of determination basically helps us understand that strength within the regression relationship, so it's not tied to any particular measurement unit. It's often multiplied by 100 that can help us get the percentage of variation explained. But basically, if we have an R squared of 1, we've got a perfect fit between our line of best fit and the data points, and if it's 0, then basically that's no relationship between the two variables. So the R squared value is equal to the RSS, this value here, so the regression sum of squares, and we're going to take divide it by this denominator here, the total sum of squares, which is the total amount of variation overall, okay. And we know how to calculate these, so we can then get this R squared coefficient of determination value. And actually, I've used some of these techniques fairly recently. So this is a paper which we published in Telematics and Informatics, which is a reasonably well-ranked journal. It's got an impact factor of about 4, which is very good. And basically what we're trying to do is we're trying to predict the actual adoption of cell phones and consumer spending on the ground simply by using satellite imagery, okay? So essentially what we've got on the right hand side here is a 10 by 10 square kilometre set of grid tiles for all of Malawi. So Malawi is a landlocked African country. It's unfortunately very poor. It's one of the 7 poorest countries in the world, and therefore it's a great place to actually carry out research, particularly remote sensing research, because there's often not a lot of statistical data that's collected on the ground. So if you're actually able to try and predict on the ground socioeconomic metrics, but by using Earth observation, well, that's a really powerful tool, okay. So within this, we basically had this quite complicated machine learning method, but the key point was that we ended up using ridge regression to try and predict metrics, and we basically ended up having the observed values in our results on the x-axis and the predicted values on the y-axis, and this produced a set of R-squared values basically for each one of these different metrics. So this was for Malawi, it was the cell phone adoption rate, and then this is Malawi, this is basically the amount that's spent on a cell phone each month. So obviously people unfortunately are very poor in this area, so it means whereas we might spend up to $80 or $100 per month on unlimited data on a cell phone plan here, we have people topping up just 20 cents a week in some of these rural parts of Malawi. And they're under the poverty line in many cases, but they will use a cell phone because it's so vital for them to do trade and to engage with other people, for example. So, and then we also produce these metrics for Ethiopia as well as Malawi. So you can check out the paper if you're interested in that particular application, rather than me just kind of throwing theory at you. So what does the regression output actually give us? Because basically we're going to go into the lab and we're going to actually look at how we run some of this. It's very simple code, but it gives us a whole load of outputs that we need to be able to interpret. Okay, so this is your standard R output here. We're going to get our residuals, we get the median, and then we get the first quantile, the third quantile, the minimum, the maximum. So it's like the 2 key box plots that we covered previously, but it's just basically to help us understand how our residuals are distributed. We also get these coefficients here, so the intercept is the A value and the beta coefficient is x1 is the slope here, and the estimate is for these values. So 4.6 is the value of the y-axis when the line of best fit crosses, and 9.5 is basically the change that you would get on the y-axis for every 1 unit increase in the beta coefficient, the x input value here. Okay, and then we have the standard error, which remember is basically the amount of unexplained variance that we have. And then we have this t-value here, the critical test statistic, and then we have a p-value over here telling us about the significance of this coefficient. So what we're really looking at here is ignore the intercept in terms of probability, just focus on this x value here, which is the input factor, and if it's significant like it is here, so the p-value is 2 to the minus 16, okay, so that's 0.00000 16 decimal places 2, okay, so very, very, very significant. And basically this is indicating that this metric that we have here is a very good predictor for the y variable that we've used within this particular equation, okay. And a good thing to look at is that if your t-value, your test statistic, is twice the size of your standard error, then you're pretty much always going to get a significant result, okay, so that's something that you might want to consider looking at. So these are all of the individual diagnostics for these input variables. This is just telling us the significance code, so we've got 3 asterisks up here, which means that we have a probability value that's highly significant. If you have no asterisks, that basically just means that you haven't gone below the 0.05 95% confidence level, and therefore you don't have a significant result, okay? And then down here what we have are the actual model diagnostics, okay? So we have the residual standard error for the model based on the number of degrees of freedom. We have the r-squared value, which is basically telling you how much variance this predictor was able to explain in the model, which is 0.54. So this is 54% of the variance in the model was explained by this predictor. We also have the adjusted r-squared, and this is basically the better metric that you want to focus on, because often as you stick more independent explanatory factors into your model, what happens is you end up inflating your r-squared statistic. So the adjusted r-squared just adjusts it for the number of metrics that you put in. So if you just have a bivariate regression like this, it doesn't really matter that much. But as you start to put in like 5 or 6 variables, you're just going to have a natural inflation of this r-squared value, which is just incorrect as a consequence. So we need to adjust it down based on the number of inputs. The F statistic is the significance of the model, which is very high, 105.2, and that means that we have a very, very, very significant p-value. It's 2.2 to the minus 16, okay, so remember that's 0.0000 for 16 decimal places to 2, okay. So I think that's all pretty much explained. Now let me just run you through some of the residuals, because that's going to be important for when you carry out your analysis. So remember, I try to emphasize all the way through this class, just because you can run the test doesn't mean that you've met the assumptions of the test. It's garbage in, garbage out, okay? So you need to make sure that if you are putting data into your model, that all of that data actually fits the assumptions, and one of those is making sure that we have residuals. So this is basically the unexplained portion, the deviation from the regression line, making sure that they actually meet the assumptions of the test. So here we have distance from a lake on the x-axis, and we have the snowfall on the y-axis. We have 2 red dots, which are basically the predicted values of y for given values of x, and then we have the blue points, which are the actual values of y for the 2 x points that we've got, okay. So if you look here at this red point, this is where we think it is, and it's 86.97. The residual is basically the difference between that 86.97 and 96 up here, so we end up with 9.03. So this is how we get this residual that's positive. And then down here we've got the opposite, so we've got this predicted residual here, which is red, which is 94.36, and then we have this residual down here, which is blue, which is 86, and if we subtract 94.36 from 86, we get minus 8.36, which is the residual value. So it's the amount of deviation that this blue point, which is the observed value, differs from the line of best fit that we fitted. And then we want to get those residuals basically, and we want to be able to plot them. So you can get the residuals by basically subtracting the predicted value from the actual value of the dependent variable. Okay. And this is really important for how we then analyse whether we've met the assumption. So we need to make sure that when we first start using these techniques, we actually have a linear relationship between the regression variables. We need to make sure that the residuals we just looked at are actually independent of one another. So that means that they're not correlated in some sort of way, or that they change over time, for example, in time series data. We need to make sure that those residuals have a constant degree of variance and that they're actually normally distributed as well. Okay, so I'll give you an indicator of what we mean by that. So here we have a regression diagnostic. We have this residual plot down here, so we have the fitted values on the x, and we have the standardized residuals here. These are plotted in standard deviations. And basically what you can see is that for some reason we have this non-linear kind of roller coaster shape. So it's like an inverted bell-shaped curve, so a U-shaped curve, which means that we're basically not complying with the requirements that our residuals are actually linearly distributed. We could also have non-independent residuals. So for example, here over time we have on the x-axis an increase in the standardized residuals. They go from negative to positive, which means that there's some sort of autotemporal correlation, unfortunately, which means that we're basically not able to meet the assumptions for the model. We could also have non-constant variance. So here we have the fitted values and the standardized residuals, and basically have this funneling out of these data points. Okay, so what you really want here is something called, and I know it's a horrible word, homoscedasticity. And basically this is a complicated way for saying that you have constant variance across this space. So if all of these points were just randomly distributed, we could be fairly certain that the results meet this assumption and that we've got homoscedasticity within our residuals. Unfortunately here we don't. What we have is the opposite, so homo being the same, whereas hetero being different. We have heteroscedastic residuals essentially, which means that we're getting changes in variance as we fit these values, which is quite concerning. So we need to make sure that our residuals are also normally distributed, and one way to do this is that we can use a normal plot which plots the quantiles expected, the theoretical residual quantiles, with the actual quantiles which we obtain, so it's called a QQ plot. And basically if you get a deviation from this line, what we're getting is a lack of normality. Okay, so if you look here, if we had all of the points directly along this line, like this perfectly normal distribution over here, then they would be Gaussian, bell-shaped distributed residuals, normally distributed residuals. Instead what we have is this wiggle here where the residuals are changing, and this is indicative of non-normally distributed residuals and means that we violate the actual assumptions for the regression test. So what's an example of a good regression? So I've shown you all of the bad regressions. Now let me talk you very quickly through some good regressions. So imagine this is the scatter plot, which before you run the fancy test, you're obviously going to look at your data distribution. And you've got x here, and for every x unit increase you have a positive increase in y, so you've got positively correlated data points here, and they're linearly correlated, which is good, which means that this is quite a good set of data, two variables to regress together. So if we look at the residuals over time, we see that they're randomly distributed. There's no sort of correlation with the spread of the residuals over time. We also have a residual plot here. Again, the data are fairly normally distributed, randomly distributed across this space, which is great. And then down here, if we look at the normally distributed residuals, there's not that much deviation from the line in this QQ plot, which means that we can be relatively certain that these residuals are basically normally distributed. They're Gaussian, following a bell-shaped curve, and we can test that if we really wanted to with a proper test statistic analysis, like we did previously with the Kolmogorov-Smirnov test. But I think here we can be fairly certain that this is conforming nicely. So, standardized residuals. So this basically enables us to actually compare between different regressions. So we can take the residuals that we got and we can divide them by the standard error to actually normalize them. Okay, so we end up with a set of values, and generally if we're getting standardized residuals that are either above or below 2 standard deviations around the mean, then this is indicative of us having outliers within the analysis. And obviously if you have outliers, like any scientific analysis, you need to decide whether you keep them in or whether you remove them. Removing them is always a challenge though, and you have to have a really thorough explanation in your analysis as to why you remove those, and in case you might just be fiddling with the distribution, which is obviously not good scientific practice. So the standard error of the regression, the residual standard error, is an index representing the typical distance separating a point from the regression line. So you've got it here, and we know how to calculate this. So we can take the ESS that we've already got, square it, divide it by the number of degrees of freedom, n-2 here, and then take the square root of this. Okay. So that was n-2 because it was a bivariate regression. Now let's move on to a multivariate regression. Okay, so this is basically where we have more than one predictor variable, so more than one independent variable trying to explain an outcome. Before we just focused on, for example, the number of years of education that you had and then the income that you command when you go into the workforce. Now we're able to do more sophisticated things. So for example, here what we could do is we could consider the amount that a plant grows based on a function of the light intensity and the length of time given for it to grow. Okay, so you can have y as the plant growth, so let's just say that this is either height or yield, so something like that. It could be, the height of the plant is one aspect, or maybe the amount of fruit that it produces, or the number of vegetable pods that it produces for the actual growth. And then for the x one, we can have the light intensity as an explanatory factor, and the length of time it's allowed to grow as another explanatory factor. So with two independent variables, you can do far more in terms of explaining your outcome variable, but you could think of this basically, because obviously you can't just have it in a kind of a 2D space, you have to think of it in a 3D space. This is like a plane of best fit, okay? And it can get more and more complicated as you include many more dimensions. So we won't be going to that much difficulty here, but essentially we'll just be using the standard ordinary least squares. So we covered this previously in this class, but we're basically assuming that these relationships are linear, okay? So we still need to have some sort of reason though in order to include any predictors within the model. So if I was going to say to you that we were going to look at income, and then we're going to collect predictors for that, choosing education, maybe parents' income as well, because that might influence your future income, unfortunately, in many ways. Also, where other factors that might affect that, such as your IQ, how hard you work, how many hours a week do you put into your work, how well you performed on your degree. These are all other metrics that we could put in. But if I then said that we were going to put in the temperature, the annual temperature for where you live, you would say, well, that doesn't logically relate, okay, to your income, not explicitly at least. So basically that would be an example where you don't really have a logical reason in order to include that predictor within your model. They need to be confined so that your independent variables basically are causally trying to indicate that they're able to explain that much variance in your output metric, okay. So bigger coefficients are not necessarily better. So the coefficients are scaled, they're not absolute measures, and you must standardize them by dividing by the estimate by its standard error. Coefficient validity, if coefficient fails its t-test, doesn't necessarily mean it needs to leave the regression. Well, it's complicated, you see. It's like you're using quantitative methods to do science, but there's an art behind it. And basically what you need to do is you need to run regressions where you place explanatory factors into the model, and you need to remove ones that maybe are less good at explaining the outcome, and you need to look at the overall adjusted R-squared and significance for the overall model diagnostic in order for you to make an interpretation as to whether you should include or exclude specific predictor variables, okay? So there are some more issues. One of those is multicollinearity. So this is always a problem. The minute that you put like, say you want to explain income and you want to put in variables for the neighborhood that you grew up in, you're going to put in population density. And then the minute that you start to put in things like the percentage of people in that neighborhood who have university level education, well, the two are going to be correlated, because generally in cities where you have a higher density of people, you probably also have a much higher density of people who have college degrees, okay? So you end up in this multicollinearity problem, and it's not very good for you in your regression to have lots of covariating data metrics. So you really need to look at the correlations between the two of them and try and remove any that are very seriously correlated together so that you can get the most explanation with the least number of input variables. It is also possible to overfit the model. This is a really key issue. So you know, just because so no matter if a new independent variable is related to the dependent error variable or not, the R squared might still increase. It might just be accounting for some random noise. So basically that's why we have this adjustment of the R squared value. But just because you're putting in lots of explanatory variables, your R squared might just naturally increase, which is an error, and we need to avoid that. So you need to look at the adjusted R squared, okay, and try not to overfit the model to the data inputs that you place. So let's see what happens as we try to see how a dependent variable tax burden is predicted by adding independent variables like GDP per capita, median age, or density. Okay, so what we basically have here is the tax burden as the explanatory variable, then we have the GDP capita, and basically what we have is metrics here, they're all significant, and essentially we're getting an R squared value in this first instance of about 0.3 with an R squared value of 0.28, and then we're going to put in more values. So here we've got GDP per capita and median age, and then basically we've got a multiple R squared value of 0.4, so basically the multiple R squared value has increased, but the adjusted R value was also increased, but it's gone to 0.37, so this is good. That was a good indicator to place into the model. It's improved our explainability of the overall model. But then as we go down here, we've got tax burden is equal to the GSP per capita, the median age, the population density. Now our multiple R squared value has gone to 0.4077, so it's higher than the others. But if we looked at the adjusted R squared value, we've actually got a lower R squared here. And so this basically hasn't actually helped us provide any greater explanatory, it provides no additional explanation for the deviations in the output variable, even though we've added in another variable. So basically you need to consider about removing one of those variables, potentially population density, and you might also, as I mentioned before, have an issue here of multicollinearity. So the minute you put population density in, if you've got something like median age, that's going to be highly correlated, because basically where you have high population density, you're going to have a much lower median age, and where you have lower population density, you're probably going to have a higher median age, because young people want to go to the city to have fun, right? And that's quite literally the key explanatory variable for why you end up having that. Okay, so if you look at New York, LA, DC probably as well, you're going to have really young populations, people who go there, they go to college, they work there in their 20s and their 30s, as they start to want to have a family, or they want to buy a house, they want to have a bigger garden. That ends up forcing them kind of away from the city, and they go and live in lower population density areas. Okay, so younger people are able to kind of put up with high rental prices, high real estate costs in order to have lots of fun and to have a high-flying job in the city. And then people often move out to the suburbs or to rural areas as they get older, when they kind of have less value in going into the city and doing all those kind of fun things. You know, how many 60-year-olds are out clubbing every week? Not many, okay? So that's a good example of why you end up having this shift. Okay, and this is just explaining now that you can put even more variables into your model, and what you'll end up with is basically a lower R squared value. So look, that's the regression part of the course, and you've got an assignment on that, so just make sure that you cover it this week, and just reach out to me if you've got any further questions, and I'll be happy to answer them. So I think that the preliminary final date for the exam is going to be December the 14th, which is going to be the time when you have to have completed it by, and I'll submit those final exam marks I think on the 15th or 16th, so that's the last date of term essentially. So basically the final exam is going to be about 2 hours in length. It's cumulative, so it'll have some parts of the other parts of the modules, but it's going to focus very much on some of the things that we've done in the last sections of the class. You will need RStudio available, so I'm going to give you examples and you're going to have to be able to run t-tests or regressions and basically produce some answers, and then you need to select those answers within the exam. So it's going to be a multiple choice, but there's going to be 6 different options. You can't just randomly pick, you have to basically know how to go into R and generate the actual tests that I'm talking about and then select the right answer. Okay. So what have we done in this course? Well, we've looked at the kind of overall data structures and the terminology around those. We've covered descriptive statistics, a wide range of different metrics, including the spatial descriptive statistics. We then went on to probability and probability distributions. I mean, a probability obviously is inherent to all of the statistics that we've done. And I know that many of you struggled with the probability distribution part, so I'm not actually going to test you on the probability distribution parts. But there will be some content, on sampling and estimation, hypothesis testing, inferential statistics, really the more advanced techniques that we've built up to through the course, okay? So you're going to need to know how to interpret p-values and do that type of thing. So we covered geographic data, including issues pertaining to the boundary delineation, the modifiable areal unit problem, spatial aggregation issues, and ecological fallacies. We covered different types of measurement data, so whether that's the standard interval or ratio you're probably used to working with, or whether it's nominal, categorical, or ordinal, so categories with specific orders. We then covered how to calculate on quantitative data, how you would estimate the central tendency for a set of data distribution, along with the dispersion and the shape of those distributions. And we looked at things like the descriptive spatial statistics, so looking at those central tendency and dispersion metrics in points data, and also looking at both relative and absolute measures for these different distributions. In probability, we looked at discrete and continuous outcomes. So discrete distributions, good examples would be the binomial or the Poisson, whereas the continuous distributions are more those that we've used over the past few weeks, so using the normal distribution and then using a z-score, okay, in order to estimate metrics of interest for how you draw conclusions from distributions that you have and values that you produce. And obviously that is kind of the fundamental for how we've done those statistical inferential tests over the past few weeks. Sampling methods, we've looked at simple random sampling, systematic sampling, stratified samples, cluster or hybrid samples, and I'll give you a couple of questions on this. I think the key part is that the CLT, the central limit theorem, is the basis for how we are then able to sample from smaller groups of entities and basically generalize those parameters that we get to the whole population in some sort of representative way. And we're able to generate confidence intervals based on how we do that sampling, okay, to provide us with some understanding as to the level of certainty that we have that the mean exists, for example, within a certain range of parameters. Obviously, we've progressed to using p-tests now, so the probability values for specific test statistics that we produce, but that's all based on these 6 classical hypothesis testing steps. So stating the null hypothesis and the alternative hypothesis, selecting an appropriate test, selecting a significance level that we want, delineating those regions of rejection for your test statistic, actually calculating the test statistic, and then basically either rejecting the null hypothesis and accepting the alternative hypothesis, or not having enough evidence basically to reject the null hypothesis. Just remember that there are specific ways that you have to actually phrase those particular conclusions about your hypothesis, and that's something which is tricky, okay? So the null is always no change, no difference, there's no effect, and then we can either reject or fail to reject it. So this is just basically paraphrasing what I just said in a more complicated way, so it's probably better you focus on the shorter case. Now, some of you have been doing some great work and producing the test statistics and the p-values interpreted correctly, but what I would like more of out of you is to then actually think of that p-value in terms of the probability of making a type 1 error. So you need to think of the size of that p-value that you get in relation to your kind of zone of rejection, and then making a judgment over whether there's a probability. You know, if it's borderline with the 0.05 significance level, you might have a higher probability of making either a type 1 or a type 2 error, and you need to kind of recognize that. Whereas if we have, we have a very, very, very small, highly significant p-value, you probably have a much lower chance of making a type 1 error, for example. Type 1 errors are important because this basically we measure this, so we basically introduce the probability of a type 1 error based on the way that we define our test, okay? So we actually need to be aware that we kind of have an impact over the likelihood of this taking place. Inferential tests, so you need to be able to pick the right test for a specific situation. So there might be a case where you have a certain number of samples, or you have a certain situation with a certain data type, and you have to get the right inferential test to be tested on. So remember, we did 1 sample tests covering both difference of means and difference of proportions. We did 2 sample tests, so the difference of means, but also the matched pairs t-test, okay, when we might have the same entities which are actually sampled twice, and that means that we're going to have different potential errors and residuals in the test, and therefore we have to use a different test to do that. And then you've also got the non-parametric Wilcox and rank sum tests, these tests down here if you don't have parametric data. We also covered ANOVA, analysis of variance, and the non-parametric equivalent of the Kruskal-Wallis test, as well as those categorical difference tests, so focusing on things like chi-squared and also the Kolmogorov-Shmirinov goodness of fit test, so thinking about whether we've got normally distributed data or not. And then also we covered correlations, so Pearson correlation for parametric data, or the Spearman rank correlation if we've got non-parametric data. We might want to convert those down into ranks and then look at the relationship between the two of them. We also went over the geographic, inferential, spatial, statistical approaches, focusing on things like nearest neighbour analysis. Is the point patterns that we've got randomly occurring, or is there some sort of other significant difference, highly clustered or highly dispersed? Quadrat analysis, joint count analysis, Moran's eye. So I'm not going to have you do calculations on any of these tests, but there will be other questions. So then today what we covered basically was the bivariate regression and multivariate regression, okay? And you need to have an idea of how we create this, how we carry out these tests, how we interpret those results, and actually think about the assumptions around the models, okay? So how do the residuals look? Are they meeting the assumptions that are required for our model? Okay, fantastic. I appreciate that we're almost at the end now, so I don't want to keep you too long, but I just wanted to say that it's been great teaching you. I've really enjoyed it. I hope you found the information useful. I know today I actually had one of my students from last term who came to see me. He introduced himself to me because obviously it was remote last term, and it was so nice to actually meet one of the people who had taken part in the class. And I do encourage you to connect with me either on Twitter or LinkedIn, or just don't hesitate to email me if you've got any questions after the class. I'm always happy to speak to students and advise or help you in any particular issues that you have, particularly if you're interested in further research or jobs doing kind of spatial statistics work. Okay, great. Well, thanks a lot for tuning in today. It's been great seeing you. You've got the final assignment, and also you've got the laboratory session coming up next, where we'll kind of cover some of that in a bit more detail. And then you've also got the exam coming up, so I think it should be fairly clear now what you need to do in order to excel. So I'm just going to be keeping my fingers crossed that you all do very well on the final exam. So thanks again for tuning in today, and I hope you have a great time. Goodbye.